All right, so here we are. This is COMSC 142, and we're down to Chapter 12, Code Optimization. So let's start with that, and then I've got a few demos to show you. All right, so there we go. All right, so we're going to talk about compiler optimizations for speed and for memory usage, and how you get these things to work. So when you compile with GCC, you can turn on levels of optimization. -0 will use no optimization, and that's what you often do when you're trying to, say, generate simple assembly code just so you can read it and understand it. But if you turn on the optimization, there's 3 levels of it that will do more and more things. So this will try to not waste too much time compiling, but reduce code size and execution time. And then down here it will do significantly increasing compile time with a lot more optimizations. And we'll talk about these. So what they already do is a few things anyway. They evaluate constants at compile time. So here you can define n to be 5 and then debug n at n minus 5. This is something you might do if there's some constant that you use many times in your program. And you could make it a variable, but you don't intend, you can make it this way, so it's used by the compiler and replaced by an immediate constant. It's another way to have some parameter you would wish to adjust. So that's one way to do it. And so macro expansions replaces this with 5, and then constant folding will notice that this is 5 and this is 5, so I can do the subtraction before I run 2. So it'll just fill it with 0. So this is just going to make more simplifications before compiling. All right, and constant propagation, of course, if a value is known at compile time, this value is set to 0 and never set to anything else, then it will just fill it in with 0 here. So it doesn't have to bother referencing an address and looking up the value of it. It'll just be an immediate value. That's another simple optimization. And removing dead code. For example, you can have code here, if 0, do this, but 0 is false. This will never happen. So it notices if code is dead and doesn't add it in there, which is nice. Although I must say, I've written programs for some of the projects where you have like a win function that can never be reached, and the compiler does not seem to be smart enough to notice that and not compile it. So it's not terribly smart about this, but I guess it can detect some simple cases of dead code. Anyway, so then you can simplify expressions. Multiply and division are slow, so you can sometimes replace them with other simpler things, like total plus total is faster than 2 times total, that sort of thing. All right, what they can't always do is improve it. Now, for example, if you choose poor data structures or poor algorithms like a bubble sort, it can't replace the algorithm with another algorithm. That would require something like an AI to rewriting your code, and actually we're getting pretty close to having that, but we don't have it yet. People that write code in AIs and use it without testing it, that's called vibe coding. And it's sort of a hilarious activity to see what happens. It's not a practical way to make working code yet. Probably will be within a few years, though. And of course, the optimization flags don't necessarily make your code optimal, and they might cause problems. So another difficult thing, we've used this, the debug flag -G adds your source code to the debugger, but if you're using optimization, then you can't use -G, so that's an issue. The optimization may cause errors because it's making some kind of assumptions about how your code runs, and they might not be true. All right, so another problem is undefined behavior, and boy, I ran into this one working on the projects. I had a assembly code that wrote 1 byte past where it should, and the weird result was it would work in many environments but not work in other environments. So that's the most common problem I find is you make, probably the most common problem is making simple algorithmic errors, like using the wrong variable name. But the next most common problem is accidentally causing undefined behavior, which is inconsistent. So here, if a is the maximum value for an integer, and then you add 1, that's an integer overflow. And so with no optimizations, it will wrap around to 0. With another optimization, it might return 1, that sort of thing. So if you have these circumstances that go beyond normal behavior of code, then you're just not sure what it's going to do. And I've seen it do inconsistent things, like the one I had, I think last time I saw you, would run in a debugger correctly with breakpoints, but without breakpoints it would not run correctly, which is pretty bizarre. All right, pointers, of course, can lead to trouble. You can have two pointers pointing to the same address. Now when you change one variable, you're actually changing the other also, and the source code compiler will, of course, not understand that. So here, if the, let's see, this one here, I'm going to take two variables, star A and star B. Then I'm going to multiply it by 10 and add B. Okay, but the optimized version will combine it here, star A times 10 plus star B. All right. So if the two parameters are, oh, but okay, this looks normal, but what if A and B are really pointing to the same variable? Then these two would be different. It says, actually, I'm not sure I completely understand why if they're pointing, oh, because I know, because you do this first, and that changes A, which also changes B. So when you add B, it's going to be adding a number that's 10 times bigger. Right, this second term will be 10 times bigger if you do it this way, but probably not if you do it this way. A good point. Yeah, these look like they're the same, but they're only the same if these really are distinct variables. A nasty little subtlety. All right, and so here's one where I get a prime. Let me bring up my code here. Let me go up here and make a directory. All right. Let me bring this over. This is my Debian Linux machine running on a simulated Intel processor on real ARM hardware. So it should work pretty well for all these projects. And let me get this code here. All right, this is some kind of prime calculation. Let's see what we got here. I'm going to download this code. Okay. And now ls-l. Okay, so I've got prime.c. So if I less prime.c, I can see what I've got. I have a helper function that gets the clock time. Then I have a function that allocates an array. Then one that prints an array. And then something that checks to see if something is prime by trying every value from 2 up to the square root of the number and see if it's prime, and then find the next prime, and this thing generates a sequence of primes. Okay, so that's a function that can take some time. All right, and it looks like you have to feed it a command line argument, which is the upper limit of the desired range of primes. And it will then look up the primes up to that number and keep track of how long it's taking to do various steps of the calculation. So we're going to first compile it this way, and then we're going to do it with optimizations. So this one will compile it without optimizations. And then I do this one, -01. And that's going to be prime 1, I think. Okay, fair enough. I see the pattern here, prime 1. All right, and then, well, -lm. I'm not sure what the -lm does, but anyway. All right, O2, prime 2, O3, prime 3. All right, so now I should have several executables. Prime 1, prime 2, prime 3, and as you can see, prime and prime 1 seem to be the same, but the next one is bigger, and the next one's smaller again, so they have different levels of optimization. And now if you run them, okay, just try one of them here. So I do time, prime, and 1, 2, 3, looks like 7. And then I send the errors to standard output, and then look for real. Should give me the real time it took to run. Looks like it's going to take a while. Now on this system I used before, it took 6 seconds. This is a simulated Intel processor running on ARM hardware, so that slows it down, so it might take quite a bit longer. And if I counted the wrong number of zeros, it'll really take too long. No, 7 zeros. All right, so anyway, it looks like my system here is going to take longer and I should use a smaller number. But anyway, as you can see, it takes a variety of different times. The unoptimized one takes 6 seconds, the optimized one takes 5 seconds, the extremely optimized one takes 3 seconds. So that's what you're going to see, improvements like that. And we're going to see how it causes improvements like that. So here's some steps. Now here's things that apply to a whole lot of things, including risk analysis and other things. If you just try to optimize something without using data, then based on your gut feelings, you're probably wasting your time. Because if you don't do measurements, you probably don't really understand what part of your code is inefficient. So it's better to measure performance and find out what part of the program is most important. So here, if I run this and don't restrict the output, and just see, it's going to tell me the time to allocate space is a couple of microseconds, the time to generate prime is 2 seconds, and that's it. So obviously the generation of primes is the slow step. So in case that wasn't obvious, that's the step you have to focus on. So here's the thing that calls gen prime sequence. Now this is going to call gen prime many times. If I have a length equals limit, it's just going to call this whole function many times, generating primes. All right. And there are a few optimizations that come to mind. One is that since you're generating a list of primes, you really don't need to divide by all the numbers up to the square root. You could just divide by all the prime numbers up to the square root. Since you are generating a series of primes, you don't need to there'll be a lot of wasted calculation there. But this calls isPrime several times, what genNextPrime does, calls to see whether a number is prime. And isPrime has a loop, which goes from 2 up to the square root, checking things. So it would seem like this square root, if you look at this loop, it's looping from 2 up to the square root of the number you're checking, and then doing a modular division here, x modulus I, which is very fast to see if it's 0. But this means every time it goes through this loop, it's going to reevaluate this square root, even though x doesn't change. So it's probably going to waste a lot of time doing this square root over and over and over when you don't really have to. So you can check with valgrind and the tool callgrind to see here, and it will tell you it'll tell you something about how long it's taking. Time to allocate and time to generate primes. There you go. So again, that's what came here, and what I'm not seeing is how to use this. Hopefully I made a note on my next slide. Not obvious to me here. Yeah, so if you do callgrind annotate, this shows that square root consumes the most time there. If you just look further down in the output, or use the callgrind annotate to analyze the output file. Okay, and this will now show you how much different functions consumed of the time. And here you see 52% was in this loop, and inside that loop, the square root was 22%. So a lot of time was consumed here, followed by x% I, which is very close. So it turns out 22.4% is doing the square root over and over, and 22.39% is doing the modular division, which you can't get away from. So you can improve your code a lot by moving the square root out of the loop. All right, so you move static computations inside a loop, outside the loop. It might cause side effects, of course. If for example, up here, if this x was changing somehow due to something that's not obvious, and you intended for it to be changed, so that then of course this wouldn't work. But in a case like this where x is really not changing, you could calculate the x outside the loop, and that would make your code much more efficient. So here's the improved code. You define a variable called max, which is square root of x plus 1, and you put max there. And now the loop does not have to keep redoing the square root. And the end result is the time to generate prime goes from 2.4 seconds down to 1.4 seconds. So you save about half the time. So that's a significant improvement. All right. And another optimization flag would allow it to switch from the square root library in C to the f square root assembly code instruction. So this must be an Intel processor. Well, I don't think you'd find this in a reduced instruction set processor, but apparently the processor has a hardware square root function, which of course would probably be a whole lot faster if you have it. but that's the kind of thing you'll find in a complex instruction set processor like the Intel. So anyway, let's try Kahoot. This should be 12A, should be here. Okay. All right. Yeah, all right, there you go. All right, let's start. All right, switch optimization replaces some variables with constant values. That's constant propagation down here. If it knows the variable is 0, it'll just put a 0 in there. All right. All right, which process is based in intuition instead of data? All right, that's of course the premature optimization where you use your intuition. All right. All right, and which process avoids repeating the same calculation many times? Yeah, that's that loop invariant code motion. Let me go back to the slides. I'm not sure I noticed that name before, but I think that's the one where you move the square root out, is the example we had. Yep, okay, that's where you move the static calculation outside loop. Just that name is a little unclear to me, but that's what it is, moving this square root calculation out of there. Okay. All right. Person will have to tell me your real name if you want your points. Because I don't think Elon Musk is taking this course, although it might do him some good. But anyway, I don't think the real Elon Musk is in fact taking this course. All right, so, there's other optimizations. Loop unrolling and function inlining, for example. And these are things where it's better to let the compiler do it because they make your code hard to read. So if you do it yourself, it's harder to read. Here's Elon Musk and Warrington. Okay, good. I'll make a note. That's fine. You can use any name you like as long as you tell me who you are. All right. Otherwise, good. Fair enough. All right. So, all right. And this, of course, is a big issue. And as I mentioned, I learned this when I did financial work. Writing code that's hard to understand is just a really big mistake. And it's true in any field, but that's where I learned it. It's far better to write code that can be understood than to write brilliant code that's a little bit faster in most circumstances. So function inlining is where you, instead of calling a function here to allocate this array, you just do it right here. Instead of calling a function that will allocate the array, you put the contents of it right here. The allocate array is just going to call this function, so you put it right there. Now you avoid the overhead of entering a function, having to make a new stack frame and save some variables and come back. That's the idea. So it avoids the overhead of a function call. And therefore, after this, it's easier for it to do these other optimizations too, now that variables are not in some other function, so it's not obvious what variables match other occurrences of this variable in the same code. All right. So you can suggest inline, that's called function inlining, and you can ask it to do that, or you can use optimization level 3 that will turn it on. And I say you should generally avoid inlining it manually. This is just what I've seen before. People will have one line that does many things, like just defines something and allocates it. This one's not too bad, but it really is two operations happening in the same line. And you can get to have very complicated lines with a lot of parentheses, doing many calculations in a certain order in one line. And although that might be fastest for the computer, it's harder and harder for the human to understand and update, and more likely that you or the next programmer working on the project will make some kind of mistake. Anyway, all right. Then there's loop unrolling, where you reduce the number of iterations of a loop. So here I'm going to go from 2 to max and do something. This is the prime number check, but maybe I should go up by 2 at a time and then do 2 calculations each time. So again, now I'll have the same number of modular divisions, modulus calculations here, but only half as many increments of the loop variable. So again, I lower the overhead. All right. Branch predictors, this is a big issue. The processor does this at many levels. It tries to guess what's coming up. In fact, modern processors, at least Intel processors, they look ahead 20 instructions. So when they're doing the first instruction, they're actually have begun processing 20 more instructions after it. And of course, a bunch of those are on the other side of an if or a branch statement and aren't going to be executed. But it's partway through executing them before it finds out that it shouldn't be executing them. That's called speculative execution. And it's turned out to be a huge security problem because often there are consequences of partly executing the next instruction that leave a clue behind, like there is a number now in a cache that wouldn't have been in a cache if you hadn't done that speculative execution, and you can find it. And this has been used to violate security boundaries many times with a whole series of attacks, one called Spectre and a whole bunch of variations of it, where you can go past a barrier, like a user land can read something only root should be able to read, or something like that, because the if statement that says you're not allowed to go there is not processed before some of the instructions on the other side have actually been executed. So anyway, it's a big issue. But anyway, there's these branch predictors, and the processor may incorrectly guess. But so this is, the branch predictors are a real thing, and so you can do manual loop unrolling, which led to no improvement on my system. That was going from 2 to 3. You can see it didn't speed up anything at all very much here. Anyway, they say don't do this by hand, unrolling loops, which is this. You know, you can do it by hand, but they don't recommend it very much. All right, anyway. All right. And I see, this is why loop iterations are more costly. Okay, right, because the processor may incorrectly guess whether the loop is ending. That's just another reason why they might expect this to be better, because the speculative execution will keep going past this bracket, thinking the loop is done when it isn't, wasting more time. So that would make this more efficient. But in practice, I didn't see much improvement in my tests. So it's a thing to know. All right, and then there's memory consideration, which is a big issue. So I think I won't bother doing this one live. If you get maxvector.c, this is going to allocate a couple of matrices and then fill them with zeros, and then take the time it took to allocate and to fill them. All right. And so you can run it, and it's going to tell you time to allocate and fill, time to allocate a vector, and time to do a matrix vector multiplication. So again, we just have various steps here, and if we give it big parameters like 10,000, it takes enough time that we can actually easily measure the time it takes to do these tasks. and then we can see how much it optimizes. So loop interchange will switch the order of inner and outer loops, and this is what we talked about last time. That makes a huge difference. If you have I and j here, and you increment I and then j, it will be much faster than this way, because it fetches large amounts of memory at a time, and if the data you're looking for is near each other in memory, then one fetch gets you several values all at once. But if you jump by big jumps through the array, then you keep having to do a fresh fetch of data every time. So of course we talked about that. That can make quite a big difference. Here it's making it almost like a factor of 8 times faster. All right. But you have to do it manually. The compiler will not figure this out for you. All right. And what's interesting is optimizing here also leads to more improvement. Up here, optimizing doesn't do any good with this original one, because the real problem is that you're accessing the elements that are far apart. Here, it's able to do some degree of automatic optimization, and I wonder how it did that. I don't really know. But I guess one thing it might do is several of these to lower the number of recurrences of the jth loop, but it may have done other things. All right. So matrix filling is the next limitation. Time to allocate and fill is 1. All right. So that made the multiplication here. This is what filling matrix looks like. It just counts all the rows and then fills it with calls elements. All right. So we can break the loops apart. So instead of filling 2 matrices here with loops, we can make 2 separate loops. Now this would seem to violate what we talked about before, where you would do more calculation in each loop, but in this case it's loading into different data locations. So if you do this, it can use multi-core processors and have these 2 cores run simultaneously, filling these different areas. So that's an optimization that you'd miss the other way. And so, all right. And another thing you can do is you can not bothering to fill the result with zeros, because you're going to fill it with the results of a calculation. So you can skip that part entirely. That's another way to make an improvement. And if you try that, it gets a little bit better, I think. Time to allocate and fill goes from 1.9 to 1.5. All right. I noticed the multiplication got much faster here, and I'm not sure why that would be. But I think that must be another aspect of the code, which I don't remember. But anyway, profiling how memory usage fluctuates is here. Valgrind will do this. If you use massif, it will measure your memory use of your code while it's running in different stages. And this is to catch things like memory leaks, where you're dynamically allocating memory and you allocate more and more. Memory leaks are extremely common. There was one in Windows 95, I remember. Windows 95 would crash every hour or two with the blue screen of death, because it would just hog up more and more memory until it died. This is quite common that programs have that flaw. So you can run massif, and it will tell you down here how much memory is used by different activities, like 99.98% is used by malloc, 99.96 is used by allocate array, and in main. So this function called allocate array is doing most of it, and so that's how you can tell what part of it is using most of the memory. Of course, allocating the array is what's using the memory, but in case that wasn't obvious, you can find out here what part of your code is using the most memory, and then if the problem is your code is using too much memory, you know what part to focus on to improve it. All right, so here's your takeaways. Choose good algorithms, of course, which we talked about in this course and the previous course. Using standard library functions is almost always the right thing to do, because those are highly perfected, and your, the code you make yourself is usually much less efficient. And by the way, in the world of cryptography, it is very, very important to always use standard library code. People keep writing their own cryptography, and you almost always end up making a mistake that makes it insecure. It is much, much better to use a standard library, because in addition to it generally being better code, also other people are using it, and there are updates and vulnerability reports and patches, so it is being constantly improved, and that's probably not true of your custom library. So use data and not feelings to optimize your code. Split complex code into multiple functions. Make your code easy to read so it can be understood. And you can check memory use, and of course your compilers are constantly improving too, so later versions of your compiler might be better at optimizing. Anyway, Let's take a look at another Kahoot. 12B is here. All right. All right. This looks like an automatically generated name. Anyway. Docker containers generate names like that. Anyway. All right, so which optimization is performed automatically at O3? Boy, I don't remember. The loop unrolling. All right. Where it puts more functions inside the loop, I think. Fair enough. Wait, no, it's the function inlining. Pardon me. Okay, the function inlining. Oh, yeah, and they talked about how that one's kind of risky. Okay, fair enough. All right. Which optimization improves the efficiency of speculative execution? Oh, okay. All right, that's also loop unrolling. That's what I thought. Let me just go back and make sure I got the names right. I have trouble remembering these names. Okay, loop fission is where you break two loops apart. Okay, and loop unrolling is where you do more calculation inside the loop to have less iterations. Okay, and therefore the speculative execution wastes less time. Okay, fair enough. All right. All right, which optimization improves the efficiency on a multi-core processor? Which everybody's using multi-core processors now. Except, I suppose, Internet of Things devices might still be using the old single core. That's loop fission. Like I say, break a loop into two separate loops so they can run on separate processors. All right. All right. All right. I've got the winners. Okay. So let me stop this recording.